To give this problem a little context, let's take a look at 2 raised to a prime power minus 1. Okay, so 5 is a prime number. 2 to the 5th minus 1 is equal to 31. Okay, and notice that 31 is prime. Now, prime and composites, I guess, can be thought of as antonyms, mean the opposite of each other. A prime number, and just I don't want to belabor this, but the only way you can decompose 31 is to write it as 1 times itself, okay? That's just the opposite of what a composite number is. And a composite number, an example would be like 12. 12 is equal to 3 times 4, right? Or you could write it as 2 times 6. But it's a composite. That's why they call it a composite. And so the general way of talking about composite numbers is this n is composite, provided that you can find factors strictly between 1 and the number itself that are divisors. Okay, that's what characterizes this. You can think of this as a definition of what it means to be a composite number. Now, this result down here is what gets us going. Notice that this result, this factoring result, is just a special case of the n equals 2 case in the very well-known difference of 2 squares formula. X squared minus y squared is equal to the product of the binomials x minus y and x plus y. Okay. Again, what you see below is a factoring formula that generalizes this idea of the difference of 2 squares. Okay. Now, how do we use that? Well, it's really quite straightforward. Now, I do have another example here where the 8 you see right here is not prime. 8 is not a prime number. We can split it up into 2 and 4. And notice that 2 to the 8th minus 1 is a composite number because 255 is equal to 5 times 51. Okay, and there's other decompositions because 51 is also composite. It's 3 times 17. Okay, but we've seen that if the exponent is composite, in this particular case, we also get a composite result when we subtract 1. Okay. Now let's look at the proof. The proof is really nice. It washes out very quickly. And y'all, I won't say too much here. We start with a composite number. And notice that because n is composite, we can utilize this formula up here. We can utilize this formula up here in this fashion. Okay? But notice right here that this 2 to the a minus 1, 2 raised to the a minus 1 is guaranteed to be greater than 1. And that's all that's required. If we have a single factor that's greater than 1 and less than the number itself, then we have composite. So you see, this is a proof, QED. We can write QED right now. Now notice the same kind of factorization would not occur if a were prime, because you could only write it as 1 times a, right? And you would not be able to get this guaranteed condition that this initial factor is going to be greater than 1, making the entire expression equal to a composite number. Okay. Again, I won't belabor that too much, but this would not work if a were prime. This would not work if a were prime. The fact that a is greater than 1 means that 2 to the a minus 1 has to be greater than 1, making it a factor of n and making n a composite number. So that's that. I hope you enjoyed it. I liked it quite a bit.